So without further ado, I'm going to try this admittedly terrifying prospect of giving Clark's talk, having just seen his slides this morning. So I'll be filling in with what I know about it, and mostly going at kind of a high level. I won't be going in any slides that go into a lot of detail. I won't be going into those details, but I'll just be sort of giving a high level view of this. So,
Jim, on behalf of organizers, I would like to say that you're probably the best candidate to do this talk, so good luck.
Thanks. I will take that good luck. Okay, so Ray for large data scale processing. So what's this talk about? It's about two things, about Ray and its ecosystem, and data processing on Ray with a focus on using Dask for data processing on Ray. This will also introduce Dask for those of you who are not familiar with it. Some of you will be familiar with it. Some of you may even be using it, particularly in coffee analysis. So a bit about Clark, not me. Clark is a software engineer at Anyscale. Anyscale is the company that is behind Ray in the same sense that the company called Databricks is behind Spark, or Anaconda is behind Numba. It's one of these things where it's an open source product, but there's a company that productizes it for particular commercial clients, and therefore they put a lot of development into it. So Clark is working on the core Ray system, focusing on supporting large-scale data processing. And before Anyscale, he was a Ray user. Ray it's a new product, but it's been out for a few years. So what is Ray, and why should you care? So Ray is a distributed task engine, providing simple API for building distributed applications. Actually, let me go higher level than this slide. So in the long view, actually, earlier Ben gave a talk showing the transition, the development from Hadoop to Spark to Rapids, where at each stage loading and unloading of data was simplified. Hadoop was sort of the beginning of this big data movement around 2006. Providing sort of a base layer, an infrastructure into which MapReduce jobs could be run. And then Spark was an improvement of that expanded upon from just map and reduce to arbitrary functionals. And it came out of the Berkeley AMP lab. Started as an academic project, Spark did, and then it became an open source thing with a lot of commercial input. Ray is the same way as that. Ray also came from the Berkeley AMP lab, or I think maybe the AMP lab has changed its name. It started as an academic project to improve upon Spark, and now it is getting into widespread use in industry. And it's improving upon Spark in two ways. One is that whereas Spark was purely functional, the workers didn't know any state. Ray is stateful. The workers in Ray can remember what has happened before, and we'll be getting into that in the next few slides. And the other is that whereas Spark was entirely built in JVMs and it has a PySpark interface, we in HEP have had a lot of trouble using all of our Python heavy and C++ heavy tools in Spark because of this bridge. And we've done it, and there are projects that have successfully done it. But this bridge between the Java virtual machine and the real machine has been a problem for us. Ray was developed in Python, so it's already native computing. Python-centric. although there are Java and C++ APIs. Okay. Right, so the Ray API and programming model. So this on the left is what is kind of what Spark was all about. These pure functions and distributing them. This is something that goes beyond what Spark can do. A class like this counter that has internal state, and so it remembers the previous value, and so when you call a method like increment, it's able to atomically increment this number and not get that wrong. In Ray, these functions are called tasks. It's the same word as is used in Spark. And you make tasks by putting a decorator, this Python decorator in front of it. Actually, that looks just like Dask. But now there's also this this actor, which is what classes with state become. And all of them are made remote by putting @Ray remote in front of it. So Ray is a collection of actors who remember their pasts. The actor model is a model of parallel computing that goes way back to the 70s. So in fact, it is widely used. There's a library in the Java and business world called Akka, AKKA. This Akka library implements actors, but this is bringing it to the Python ecosystem. And I guess you can also specify a number of GPUs. That's nice. Of course, I don't know the details of how you use that. So the principles of this, the bottom substrate can be a number of systems that are already out there. There are, so AWS, Google Cloud Engine, Azure. These are all clouds. Kubernetes, you can run this thing on Kubernetes, and you can run it on a laptop. So you can do your small scale testing on a laptop and then scale it out. That's just like Spark. That was a good idea. So then they break the architecture of this into an autoscaler with the high level task actors that you create in your program on top of that. And actually, when I say you create in your program, this might actually be like the coffee developers or other framework developers making frameworks for HEP. I'm not sure whether individual physicists are going to be writing to this API or not. Okay, great architecture. And here's where I'm not going to go into details because I really wouldn't be able to do this justice. One thing I can say about the Ray architecture is that unlike the Dask distributor, the Dask scheduler, there is no single point of failure. This is something that people who are developing distributed systems think about a lot. Single point of failure. If this one node dies, does the whole cluster die? That's a single point of failure. With the Dask scheduler, there is one scheduler task, and if that task dies, the whole job is gone. Ray was developed with the idea in mind that we're going to have, well, first of all, multi-user systems, and therefore they have to be robust. You can't have one user, taking down the system. Whereas Dask's point of view is that one user creates a system, uses it, and takes it down. So Ray is really built from the ground up to be one of these large multi-user systems. Okay, details of what the clusters look like. Raylets, I suppose, are pieces of this. I'll just zip on past the details. So comparisons to other systems. So we have stateful computation, that's new. Actor fault tolerance. The performance, millions of tasks per second, millisecond latency. So these are the actors have to be very lightweight. Shared memory, zero copy serialization. This is done with Apache Arrow. which you've probably been hearing quite a lot about recently, because it allows for nested data structures to be zero copy, serialized, and shared among processes and across networks. And arrow data structures have a one-to-one relationship with awkward arrays. So conversions between them can usually be zero copy. So that's another reason, what the data that we're sending around between these things is arrow. So it's efficient to move data across. And that's part of the problem that we were having with Spark and PySpark. Yeah, multi-language, C++, Python, and Java. And Java's still in there because business intelligence really needs that in industry. Why is Ray great for data processing? I think I could talk about this. The heterogeneous resources, meaning CPUs and GPUs, and different kinds of hardware, which we're going to be seeing more of in the near future. Distributed in-memory object store. This is the Apache Arrow that I was talking about. Part of the Arrow project is a memory store called Plasma that very quickly moves Arrow objects around among processes. And FastSmart decentralized scheduling. This decentralized scheduling is the zero point of failure that I was talking about. Okay, so given that, you might need to say that this task requires so and so many CPUs, or it requires a GPU. We can put those kind of requirements on a task, so it'll go to hardware that actually has that, or it needs to have enough memory or whatever. And this is talking about the object store. This is the Plasma object store, which is what allows for zero copy reads on the same node of workers using shared memory. And the reliability is that if not everything fits into the memory of this object store, it spills to disk. These are details that I will not be able to speak to. Ray ecosystem is focused a lot on ML and distributing ML, machine learning, I mean, which will be of interest to a lot of people here. All right, now Dask on Ray. What is Dask? Dask is a parallel computing library for Python geared towards scalable analytics. And they provide parallel NumPy array and data frame abstractions, and in the nearish future, awkward array abstractions. That's something that we're going to be working on. And so these provide the same interfaces as NumPy array and pandas data frame and eventually awkward arrays, but do the computations in a distributed way. As a user, you see this only in one place, where at the beginning you say, these are distributed objects. Your whole computation on it is just is a description of a computation. And then when you say .compute, then it actually runs it all. And when it runs it all, it can run it all in a distributed way. Is this an example of that? This is kind of an example of that. We import Dask array as DA, and then use this Dask array as though it were a NumPy array. Or we use this Dask data frame as DD, and we use this data frame as though it were a data frame. I guess this is a scikit-learn integration, which is great. I was just answering a question about this yesterday, that scikit-learn has to be in on it, has to be aware of these, the fact that your data is distributed in order to implement a distributed algorithm on them. So So with these interfaces, they all know about the fact that this data is distributed. All of these steps in the process, like x plus x transpose minus x mean, all of those are just accumulating a set of instructions of what you're going to compute. And then at some point you say dot compute, and it actually runs it. And where it actually runs it, whether on your local machine or distributed across your local machine or distributed across a cluster, is something that you can configure separately from actually doing the calculation. So you get to separate your analysis code from how you run your analysis code. And that's great because you can test it on your laptop and then run it on a cluster. And so Dask's three main components is it has these collection types, Dask array, Dask data frame, Dask bag. Dask delayed, this is just labeling a function as delayed. This is actually just like Ray's remote function, remote task. And then in the future, there'll be another box here called Dask awkward array. So there's these collection types. You do stuff on the collection types and it creates a task graph, a set of instructions of what you want to compute and the dependencies among all of those steps. And then it goes to schedulers, which could be single machine or distributed. And that's what actually runs it. Do you run it all on your local machine or do you run it distributed? And the thing is that Dask has already implemented all of this great stuff. And its scheduler, as we'll talk about on a slide that's coming up, is a bit lackluster, designed with single user scientists in mind. And we can just, because of the modularity of all this, we can just replace this one piece with Ray. So that's what this Dask on Ray is. So some more detail about what a Dask graph specification looks like. This is using Dask delayed, where you can delay these functions. You can delay like the increment and the add function using a decorator. And then when you call them and you say that this, if you say at Dask delayed of this def inc, then when you call inc on X, it's not going to run it. It's just going to add it to the task graph. And this is what that graph looks like. The Z, which is the result of this that you want to see, consists of adding Y to 10, and Y consists of incrementing X, which is 1. And then when you say Z.compute, you get the actual value of Z computed on some system. Task scheduling and execution. This is this is the thing that we're wanting to fix here. So what are we saying about this here? Dask provides several scheduler options, a local synchronous scheduler. So that's like running things on your laptop. A local multi-threaded scheduler using a thread pool, or multi-processing scheduler using a pool of processes. The difference between a thread pool and a pool of processes, both of these are running on your computer. It's just a question of whether you have only one Python process or multiple Python processes. And generally, you'd want the multiple Python processes because Python has a GIL, a global interpreter lock, that will prevent good parallelization with threads, unless most of your computation is in compiled code. And then a distributed scheduler, and that's really what we're focusing on here. This is for the big jobs that are going to go across a cluster. The architecture is that you have a client. This is you running your thing, and then the scheduler is the thing that you remotely send the task graph and the data to, and the scheduler splits it out to workers. And as I was saying with the single point of failure, if this dies, then there's no way to get the data back from the workers to the client. So the pitfalls of Dask distributed. So this global distributor is both a bottleneck for data streaming through, and a single point of failure. So there's no scheduler fault tolerance. If it's dead, the whole thing's dead. Maintenance inspecting the task graph state adds overhead. The scheduler is written in Python and inherits Python's performance characteristics, so like the GIL and also just running anything in Python. And can't be natively scared, would have to resort to sharding schedulers. I don't know what that means. These clients are, oh, yeah.
So just so you're aware, you've had about 25 minutes.
Oh, yeah.
And there's two questions on the slide.
Oh, yeah, I should do that. And actually, have I said everything that I want to? I might have just done that. I might have made all the points that I can legitimately make. Actually, I really want to show this. All right, where's the question? There's the questions. So let me talk about this. So questions. How would you compare Ray to, e.g., Nextflow or SnakeMink, given that you know these frameworks? Well, I don't know these frameworks, Nextflow or SnakeMink. Is there support for batch systems like, I didn't see that listed in the slide, whether there's PBS, Torque, Slurm, so actually, I don't know if traditional batch systems are going to be able to provide enough of a interface for Ray to be able to do what it needs to do. I think that the most promising option for it is the fact that it runs on Kubernetes, and a lot of our HEP ecosystems run the new ones. You know, a lot of new developments are being developed on Kubernetes. So I think that Kubernetes might be the way that we run this. But that's very much a non-expert opinion, and I don't know what Nextflow or SnakeMink are.
Yeah, about this.
Okay, good. Yeah. Please do.
Oh, sorry. So hi, I'm Nick. Jim pulled me in here to answer Dask-related questions. I thought I'd chime in here just to say that this is maybe one example where Dask, and this kind of addresses the next question, is one example where Dask has a bit of an advantage over Ray is it's simpler in some sense. It's like a pure Python set of server client systems. So putting it on top of batch systems is very easy. And there is Dask on Slurm, Dask on PBS, Dask on whatever, you name it. Whereas Ray has more of a, a service architecture, right? Where there's these persistent services like the object store and the various multi-scheduler systems and the message passing. And so in that sense, Ray may be a little bit more difficult to set up than Dask on a given set of resources, especially if the only way you have to access them is through a batch system. Now, that said, I wouldn't be surprised to see Ray on batch because people, I believe, have even managed to make Spark deployable on batch. And I don't think there's anything more difficult to deploy than Spark at this point. So it's probably possible if someone takes initiative, but I don't think it's their lowest hanging fruit. They're probably much more interested in making it deployable on Kubernetes, which is what's more in the wheelhouse of Ray. So.
Yeah, and then even if it turns out to be possible, that might kill the performance that you wanted from it. I don't know. So actually, I really don't. Yeah, so I don't know. And it's worth checking with Dask to find out if they have these kinds of backends, and I just don't know about them. If that's totally possible. I want to answer this one because it's easy. Ray is it free software? Yes, it is. Yes, it's free, just like Spark is free. So how about this one? Personal suggestion for HEP projects in the HEP ecosystem, what should be a preferable choice for scaling, Dask or Ray? Well, the thing that I was very excited about this project, and the reason I wanted Clark to speak about it, is because we can take the best parts of both. Also, I think that these questions of whether the system is being distributed by Dask or by Ray or by, you know, I can't think on my feet, is something that is usually one step away from the physicist. People are designing these query services to set up a system so that at Nebraska, for instance, there's the Coffee Casa project, which I believe is using Dask, and so as a user, as a HEP user, you would submit your work there, and tools such as Coffee insulate you from the choice of backend scheduler. But so that much said, what I think should be done here is that Dask was designed around the task graphs. This is Dask's sweet spot. This is what Dask does really well, is the task graphs and the collection API. It is a fact that the scheduler was an afterthought. It was added because they said, well, if there is no scheduler, then what are people going to use these task graphs for? And that was the spirit in which the Dask scheduler was developed. Ray is focusing just on this distributed problem. So I think they dovetail together perfectly. They should be used together in exactly the way that Clark was describing. There's a question here. What about data provenance? Workflow managers offer tracking of how data is mangled. Do you mean managed, maybe? Activity, user, entity tracking. Does Ray offer such functionalities? That is the sort of thing that would be built as a higher level thing on top of Ray or any such scheduler. And the fact that Ray has state, I think is going to make that easier. It's going to make that more performant. This kind of tracking, and particularly, even if you're thinking, oh, all of my functions are pure functions. I take data in, and the results out are a pure function of the data in. There's still a lot of complicated things that need to go on, like caching, in order to do that well, and then wanting to send jobs to where the data is already cached. Those are all very stateful things, even if your physics process is not itself stateful. And I think that some of this data provenance is also stateful and can benefit from this model.